there's a surprisingly useful convention for writing out repeated operations. And one of the big surprises to me was that early in the development of computer languages, this was not built into the language, but almost everything since about 1975, no, earlier, has this built in. And so this is something that had occurred in mathematics before there were computer languages, and then continues in mathematics. So this is something that applies both to studying mathematics and to studying computer science, and it's about repeated operations. And so the situation that happens, this first came up in mathematics, and so that's the one I'm going to illustrate first, is a situation like this, writing out a series of numbers, and I'm using a bunch of notational conventions, so let me explain what's going on. So suppose I need to do this sum. I've got 1 plus a half plus a third plus a quarter. The dot 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 means continue in the same pattern. That means you have to recognize the pattern. There's no help with that. You've got to just recognize the pattern. And then the last one here is 1 over 10. So this is a repeated operation. I'm going to take some sum and keep adding numbers to it. And we would like to express this in a nice compact way. And so this is the mathematical convention for doing it. First of all, we're going to use the standard mathematical symbol for summation, which is a capital Greek letter sigma, because sum, sigma, sigma, sum. And so one of the things you got to do is write this 100 times, just so that you get used to doing it. I've taught kindergarten. Do you know that people need to be taught to write letters? Here's a new letter to write. You need to be taught how to write it. So you start at the top, and you a little serif, and then boop, 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 and then down to do that. So you do that 100 times on your own time. The other convention is that we have to have an index, and the index is where things can get a little bit tricky sometimes, because a lot of them will do. So what you have to do is number the terms, and so I'm going to give them numbers in the most obvious way. I'm going to say I have term 1, term 2, term 3, same pattern, up through term 10. So I've done the term number in red, and that's the situation. And each term is 1 over the term number. So I'm going to do that in red as well. We need a symbol for the terms. Let's call them, call me crazy, N. So the term corresponding to slot N is 1 over N. Slot 2 is 1 over 2. Slot 3 is 1 over 3. Slot 10 is 1 over 10. So what we have here is that we're adding up the individual terms are 1 over N. So sum 1 over N. And you can see, the sigma symbol is roughly 3 times the size of the font that you're using for the terms. Okay. And then you got to figure out, hey, what's the first one? What's the last one? And so this one, I said, well, my first one was term number 1 and my last one was term number 10. So on the bottom, we write n equals 1. That indicates the starting point. And the top, we write 10. We don't write n equals 10. We just know that n goes from 1 to 10. Now, this is a funky kind of notation because I'm just going to write the same thing again. This is 1 over k, as k goes from 1 to 10. So the n or the k, those are just placeholders. What really happens is we're seeing the set of numbers from 1 to 10, the set of whole numbers from 1 to 10, and we're going to add up over all of those. And so what you call it doesn't matter, but you have to use it consistently. So I called it n, I called it k. The terms are 1 over n or 1 over k, respectively. Okay. You could also number these differently, and so let me just kind of jump to the final result. You could say this is the sum from j equals 0 to 9. Now, that's the way things happen in computer science, is that you often start counting at 0. That's what computer scientists do. Mathematicians start counting at 1. And so, and now we have to figure out what each term is. And the term corresponding to j equals, j equals 0 looks kind of hard. Let's skip ahead to j equals 1, and it's 1 over 1 plus 1. When j equals 2, it's 1 over 2 plus 1. When j equals 3, it's 1 over 3 plus 1. And now if we go back to this, I should have actually written that as 1 over 1 to keep the pattern. So let me fix this. Don't do the simplifications. It's just bad. You lose the patterns when you do the simplifications. I should have written 1 over 1 right here. Anyway, so now when j is 0, this is 1 over j plus 1. And so we get the same series of numbers expressed very differently. So here are 3 ways to look at this series of numbers. There are many, many, many more, but that's the way it goes. Okay. There's an interesting series of numbers that is worth mentioning. The more often you see this, the better, because this is one of the foundations for doing so many hand calculations. And so I'm just going to give you a piece of this. J equals 0 to n of 1/2 to the n. So this is called a geometric series, and the general term is 1/2 to the, excuse me, it's not 1/2 to the n, it's 1/2 to the j. 1/2 to the n would be 1/2 to the n, 1/2 to the n, 1/2 to the n. This is 1/2 to the 0, which is 1, 1/2 to the 1, which is 1/2, 1/2 to the 2, which is 1/4, and so forth and so on. And this is something that the sum is actually well known, and so you can, when you recognize this, you can first of all, you can write it correctly, excuse me. When you recognize this, you can just skip straight ahead. And so I am writing it out. It's a little complicated. It's a fraction. The bottom is 1 minus 1/2. That's the same 1/2 as in here. And the top is 1 minus 1/2. So the n plus 1 power, 1 more than the top situation here. So here's an effective sum that gets used a lot. And so, so there it is. Okay. One of the things that happens is that we've got kind of a convention here. What we did is we took the symbol for sum, this capital Greek letter sigma, and we made it big, and then we put an index starting, you called it, say, j equals a start point, up to j equals an end point. And so it works out that you can do this with any other mathematical operation. And so I want to look at some examples of those because those keep coming up. And so the first one I want to look at is union. So if we have 2 sets, we know how to take their union as just something that's either in one set or the other. So that's a typical union. The U is kind of small, but that's okay. But then we could take a whole bunch of sets, and I'm going to do a specific example that can be very useful on the mathematics side. And so what you do is you make the U really big. That's the convention. You take the symbol, you make it really big, roughly 3 times the size of your general term. So you make it really big, and then you have an index. And in this case, I'm going to use the index I, and I is going to go from 0 to 9. So this is going to be a union of 9 sets. Now I can specify them by giving them a subscript, but I'm actually just going to specify them by saying what they are. And I'm going to use the example of closed intervals, which you've seen in pre-calculus, and so everyone who's watching these has taken pre-calculus. So I'm going to use the closed interval. So the symbol for a closed interval is to include things in square brackets with a comma in between. And the endpoints in this example are I and I plus 1. So this is a union of closed intervals on the number line, and there are 10 of them. When you go from 0 to 9, that's 10 actual terms. And it's really helpful in a lot of cases to write out a few of these. So this is 0, 1, union, 1, 2, union, and then you always do the last one. And the last one is when, let me show you what I'm thinking about here. The last one is when I equals 9, so that goes from 9 to 10. As you can see, to write out the individual sets and to say, oh, I'm going to take the union of this and this and this and this and this, that's a pain. So it's much easier to say the same thing by using this more compact summation notation. It's not a sum, but people still call it summation notation. So that's the union. Now this is an interesting thing. If you look at a number line, what you're looking at is the interval from 0 to 1, and then we're going to take the union, so everything that is included from 1 to 2, and then we're going to take the union, everything included from 2 to 3, and again I'm going to use some dots here to show what's going on. So we're going to take this interval, union this interval, including the endpoints, union this interval, and the last one is goes from 9 to 10. I didn't write it correctly, sorry, from 9 to 10. So you have this piece of the number line, piece of the number line, piece of the number line. And we're taking anything that's in any one of those pieces, and that works out that that's just the closed interval from 0 to 10. So you just union them all together, boom, 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 and you get the interval from 0 to 10. We can do a similar thing. I'm going to use a different example of the sets. You can take a big intersection, and so what I do is I take the symbol for intersection, make it 3 times as big, and this time we're going to use the closed intervals between 0 and 1 over I. So I is the index, and I goes from 1 to 10 this time. You know, if you want, I can go from 101 to 110, or I can go from anywhere. The point is to get 10 things, but then you have to adjust what's going on in the formulas inside to use the I that you have. And so here, well, it's always good to write out a few of them. So the first one is the closed interval from 0 to 1 over 1, and then the closed interval from 0 to 1 over 2, and the last one is from 0 to 1 over 10. There's a convention when you're writing these out. You say, oh, here's the thing, intersect, here's the thing, intersect, and then the dots, and then it's intersect again. So you put the operation that you're doing on either side of the dot, and you get this, and that's the thing. Now the thing is, this time it's intersections, and so we want something that is in all of these sets. So just kind of a little set review, that's what intersection means. And what we're seeing here on the number line is we're going to go from 0 to 1, and then wait a second, the next one we're going to go from 0 to a half, and then wait a second, the next one we're going to go from 0 to a third. And so even with just these 3, something that has to be in all 3 of these sets, I'm doing the color to indicate. Actually, let me draw in intervals just to make it clear what's going on. It's never really clear, but as clear as we can make it. So I've drawn 3 intervals here, and we're looking for numbers that are in all 3. Well, that means they have to be in the smallest one. These are, sometimes people say these are nested, and so so the original one that we have is just the last thing. It's the closed interval from 0 to 1 over 10. So that's this part right here. Okay. In math, not so much in computing, but in math, you might have to deal with infinity. There is no infinity in real life, but there is in math. I guess I just said that math isn't real life, but don't tell anybody I said that. Okay, so I want to show you a couple of examples of doing this. So again, you take the operator, you make it 3 times as big, start, end, and then what it is that you're doing it to. So I'm going to take the intersection, really big intersection symbol. And we're going to be looking at the closed intervals, from 0 to 1 over I. And we're going to go from I equals 1. That's the start. And we're never going to stop. We're not going to infinity. This just says we're never going to stop. Now, as you intersect these, you're looking at the interval from 0 to 1, then the interval from 0 to a half. It's got to be in both of those, so it's got to be in the smaller one. 0 to a third, 0 to a quarter, 0 to a fifth, 0 to a sixth. We're running out. And eventually, all that happens when you do this massive intersection is you end up with just the single point 0. And now comes something a little bit strange, is if you do the same thing, but switch from using closed intervals to open intervals. So let me show you what the difference is here. Open intervals are done by round parentheses, closed intervals are by square. So this is the intersection of the closed intervals. This is the intersection of the open intervals. And now what you get is the open interval from 0 to a half intersect with the open interval from 0 to a third. Well, that's the open interval from 0 to a third. And then, oh, no, it's 0 to a quarter. No, and then eventually anything that any number you would think of will be excluded from this because there's going to be a 1 over. That's the Archimedes principle. So you get a 1 over n that's smaller than this, and so this massive intersection is empty. You intersect a lot of things, you come up with nothing that's common to all of them. That's almost common sense. So the big situation is you take a symbol for the operation, make it 3 times as big, and you have to make sure that you get the proper terms, and you can do that with many other operations. And this has just been a super useful thing in math and in computer science.